welcome to another CHEM271 tutorial. This one is about enzyme inhibition. So there are two types of enzyme inhibition. There's irreversible and reversible. So irreversible inhibition means the dissociation of the enzyme inhibitor complex is slow. So what an inhibitor is doing is it's binding to the enzyme and preventing it from turning substrate into product. And there are a few different mechanisms through which this can happen, but the two types here, irreversible and reversible. So it's irreversible when the inhibitor binds to the enzyme, it can't really unbind. It's kind of stuck there. So this is due to some kind of covalent bond. So once the enzyme binds the inhibitor, it doesn't really reverse much due to some kind of strong covalent interaction. On the other hand, we have reversible inhibition. This is when the inhibitor readily dissociates from the enzyme inhibitor complex. And this is what you're going to see a lot of in CHEM271. So the enzyme and the inhibitor bind, they form the enzyme inhibitor complex, but this can readily dissociate and the inhibitor can be released. So this is due to some kind of non-covalent interaction, usually. And then from this equilibrium, we can get the Ki. So this is sort of like the inhibition constant here, Ki. So this is, remember, product over reactant. So concentration of EI divided by the concentration of E times the concentration of the inhibitor. And because this is just an equilibrium constant, a larger Ki means it's a better inhibitor. There's more enzyme inhibitor complex formed. So for these reversible inhibitors, we have three different types: competitive, uncompetitive, and non-competitive, which can be pure and mixed. For the context of CHEM271, you just need to learn about pure non-competitive inhibitors. So we're going to go into each of these three individually next. All right. First up, the competitive inhibitor. So the competitive inhibitor competes with the substrate for binding to the active site. So here's an enzyme. This little divot here is the active site, right? The substrate binds to the active site, but the inhibitor also binds to the active site. It binds in the same place. So what does this do? Well, Vmax stays the same because eventually if you add enough substrate, the substrate will completely outcompete the inhibitor. There's so much substrate that the inhibitor really can't bind to the active site and inhibit the enzyme. So Vmax stays the same, but more substrate is needed to reach Vmax because you need enough substrate to sort of outcompete the inhibitor. Km, by that logic, increases. Why? Because more substrate is needed to fill 1/2 of enzyme active sites with substrate, right? So you need more substrate in order to get to that 1/2 active sites full because there's inhibitor also entering the active site. So if we're looking at these hyperbolic curves, this is just a normal curve. When we add the inhibitor, we get to Vmax much more slowly, and Km sort of increases as a result of that. Okay? Now sort of looking at here, so this is our Michaelis-Menten reaction, but if we add in the inhibitor, we see we have a Ki here, where the inhibitor binds to form the enzyme inhibitor complex, and then this just inhibits the reaction. So when the inhibitor's bound, the substrate can't bind, no reaction. But if we add enough substrate, that can cause the inhibitor to leave and the substrate can bind and we can go from EI to ES with enough substrate present. So looking at the Lineweaver-Burke plot now, so without the inhibitor, we get this line. With the inhibitor, we get this line. So notice the slope increases. However, the y-intercept stays the same. Why? Because Vmax doesn't change. So the y-intercept is 1 over Vmax. That stays the same. However, if we look at the x-intercept, it gets closer to 0, so it sort of decreases in magnitude. That's because Km is increasing. So the increase in Km means the decrease in the magnitude of -1 over Km apparent. Km apparent means the new Km we observed with the inhibitor. So the Km will change with the inhibitor, it will increase. And if we figure out what that increase is, so if we know the original Km and the Km apparent from doing some experiments, we can use this equation. If we know what the concentration of the inhibitor is, we can calculate Ki. We can calculate the equilibrium constant here for the inhibitor binding to the enzyme. So that is all the details for the competitive inhibitor. Now moving on to the uncompetitive inhibitor. All right, next up, uncompetitive inhibitors. So these are inhibitors that only bind to the enzyme substrate complex. They do not bind at the active site, and they do not impact substrate binding, but they instead reduce the Kcat, so the catalytic efficiency, or not the catalytic efficiency, the rate of reaction, the rate of conversion of substrate to product. So you see the substrate binds to the enzyme, and the inhibitor binds somewhere near the active site. So the substrate can still bind to the active site, but the inhibitor is preventing the conversion of substrate to product. So what we're going to see is a decrease in Vmax. This is fairly straightforward. It's because Kcat decreases. So if Kcat decreases, then the rate of substrate to product decreases, Vmax decreases. Okay? Km decreases as well. This is a little difficult to understand because a decrease in Km usually means a better enzyme, right? Because it takes less substrate to fill 1/2 of all enzyme active sites. So what's that about? This is because of Le Chatelier's principle. So remember Le Chatelier's principle, when you remove something from an equilibrium, the equilibrium shifts to produce more of it. So whenever the inhibitor binds the enzyme substrate complex, what's going to happen is the formation of the ESI, but that reduces the amount of enzyme substrate complex. So the reaction shifts in this direction to produce more enzyme substrate complex. So essentially there's more enzyme substrate complex being produced than usual. So because of that, it seems like there's more substrate binding to the enzyme, and it takes less substrate to bind 1/2 of all enzyme active sites. It's a little counterintuitive, but you just have to remember that it's Le Chatelier's principle. Okay? The interesting thing here, though, is that Km divided by Vmax remains constant. So we can see that on the Linweaver-Burke plot. These two lines have the exact same slope. Okay? So here we go. So we see the Km apparent decreases and Vmax apparent decreases. So the curve goes down, but it also shifts a little bit this way. So looking now at the Linweaver-Burke plots. So with the inhibitor, we see the Vmax apparent increase. So that's a decrease because this is 1/Vmax. So when 1/Vmax increases, Vmax decreases. And similar here, when -1/Km apparent seems to increase in magnitude, we know that that's actually a decrease in Km apparent. Okay? And looking at here, we can see that Ki in this case is the enzyme plus the inhibitor binding, or the enzyme substrate complex binding the inhibitor to form the enzyme substrate complex bound to the inhibitor, the ESI, and this is not able to catalyze the reaction. This is inhibited. So because Km and Vmax are both affected here, we can use two equations to calculate Ki. So Km apparent, you find this from an experiment by trying to get these two graphs and comparing them. So Km apparent is equal to Km divided by 1 plus the concentration of the inhibitor divided by Ki. For Vmax apparent, it's actually the same equation, just sub out Vmax for Km. So Vmax apparent equals Vmax divided by 1 plus the inhibitor concentration divided by Ki. So these are things that you can experimentally calculate to find this equilibrium constant here. So the next one is non-competitive inhibitors. Great. Last up, pure non-competitive inhibitors. There's also mixed non-competitive inhibitors. I'll explain that in a bit. For CHEM271, you just need to understand pure non-competitive inhibitors. What are these doing? So these inhibitors, they are not binding to the active site. They are binding to a separate regulatory site on the enzyme. Okay? So here, they'll bind not to the active site, but to a separate site, and the inhibitor binding will change the shape of the active site such that the rate of reaction decreases. Okay? So I already spoiled it, but Vmax decreases. Why? Because Kcat decreases, so there's a decrease in the rate of the conversion of substrate to product. Okay? You can also think about this as the rate of reaction when all enzyme active sites are full will be less than without the inhibitor, because the inhibitor will slow down the rate at which the enzyme is able to catalyze the reaction. Km, however, is constant. Why? Because substrate binding isn't really affected by this. The substrate can still bind to the active site just fine. However, the sort of rate of reaction when it binds decreases. Okay? So the rate at which substrate is converted into product decreases. Substrate binding is not affected. So it does not impact the substrate's ability to bind 1/2 of all the enzyme active sites. Okay? So we can see here, Km stays the same, but Vmax apparent is lower. So looking at the Linweaver-Burke, we see the same thing. 1/Vmax apparent is increased, which we know means Vmax apparent decreased. So this is kind of where we get into pure versus mixed. So in a pure non-competitive inhibitor, the inhibitor binds the enzyme the same without the substrate or with the substrate. So these Ki's here are the same. Okay? but sometimes these KIs can sort of be different, so it binds the enzyme without the substrate differently than it binds the enzyme with the substrate. For CHEM271, you don't need to worry about that. That will make this a lot more complex, and you will see changes in Vmax and Km that are a lot more complex. So for the sake of this course, it binds the exact same to the enzyme without the substrate or with the substrate. Okay? And then if we want to calculate Ki, what we do, this is the same as uncompetitive inhibitors. Vmax apparent equals Vmax divided by 1 plus the inhibitor concentration divided by Ki. So that is it for the 3 types of inhibitors that you need to know. We're only doing one practice problem this time around. This is adapted from problem 30 from your textbook, from the enzyme inhibition chapter. Before this, there's a whole calculation where you need to find Vmax and Km with and without the inhibitor. We're just going to skip to the answer for that part and then move on to part B and part C. Okay? So for part A, we're just trying to figure out the type of inhibitor. So for this problem, you had to calculate these on your own, but I already calculated them here. So you find that Km is the same with no inhibitor and with the inhibitor. So it's 10 micromolar. However, Vmax decreases a lot with the inhibitor. So if Vmax is decreasing but Km is the same, this means it's a non-competitive inhibitor. Right? So non-competitive inhibitor. Next up, we need to find the Ki given that the inhibitor concentration is 100 micromolar. So because this is a non-competitive inhibitor, we can use Vmax parent is equal to Vmax over 1 plus concentration of the inhibitor over Ki. So now we need to do a bit of algebra to solve for this. So 1 plus the inhibitor over Ki. This is actually just this part right here, this is the fraction, equals Vmax over Vmax apparent. So what we did was we divided this and then multiplied this up here, okay? And then from this, we can get inhibitor concentration over Ki is equal to Vmax over Vmax parent minus 1, right? And then we can then finally find that Ki is equal to the inhibitor concentration divided by Vmax over Vmax apparent minus 1. So now plugging into this, we get 100 micromolar over 45 for our Vmax divided by 9.1. I'm going to not write the units because they would just cancel here anyways. Minus 1. And if you put this in your calculator, you get 25 micromolar. But actually, this is an equilibrium constant, so it doesn't have units. So 25. So a bit high, so it's a pretty good inhibitor. As you can see by it, really reduced the rate of reaction. So this last part's a little tricky. So if the substrate concentration is 30 micromolar, what fraction of enzymes are bound to substrate with and without the inhibitor? So to do this, let's first do no inhibitor, and then over here we can do with the inhibitor. So the equation for this, FES is equal to V over Vmax, which in this case is, so I put the rates here, so without the inhibitor 33.8, with the inhibitor 6.8. So without the inhibitor we get 33.8 over 45. The units will cancel. This gets us 0.75. We can also use the other equation here. FES is equal to substrate divided by substrate plus Km, which is equal to 30 over 30 plus 10, and we get the same answer. Both equations work just fine. You can use either. With the inhibitor, FES is equal to V over Vmax. Okay, so here we get 6.8 over max of 9.1, and we get 0.75. It's the same answer. And if we do this, down here, so FES is equal to substrate over substrate plus Km, we see they have the same Km, and the substrate concentration is the same, so we still get 30 over 30 plus 10 is equal to 0.75. Huh, it's all the same. Why? Because it's a non-competitive inhibitor. So with non-competitive inhibitors, we said that the substrate binds the same with or without the inhibitor. So because of that, regardless of the presence of the inhibitor, we've shown it's the same amount of enzyme binding, and that's because Km doesn't change, right? So that will be it for this lecture, right? So next time we will be going over 2 different practice midterms, going over all of this material and a bit more, a bit of chemotrypsin and ATCase. So see you guys then. Thank you.